In this lecture, I want to go over example 10.3 from the book. Essentially what we want to do is we want to find potentials. So find V and A for a moving charge with a constant velocity. Okay, so we'll write out the path that it takes, W, with respect to time, is just the constant velocity times the time. That's just kinematics. So I can write down the position now as r minus v times the retarded time, which is equal to c times the time minus the retarded time. So basically that distance that it the distance that it can travel is the speed times the time. So if I work out the absolute value, what I would get is r squared minus 2r dot vt r plus v squared tr squared, and that's equal to c squared t squared minus 2t tr plus tr squared. Okay, solve for tr. Let's find out what the retarded time is. So when I do that, what I get is c squared minus v squared tr squared plus 2r dot v minus 2t c squared tr plus c squared t squared minus r squared is equal to 0. Okay, so now if I solve this with a quadratic equation, tr is equal to 2 c squared t minus r dot v plus or minus the square root of 4 r dot v minus c squared t quantity squared minus, this is still under the square root, 4 c squared t squared minus r squared times c squared minus v squared. So that's still all under the square root. And then divide that whole thing by 2a, which is basically c squared minus v squared. Okay, so that looks kind of weird, but we can kind of clean it up a little bit, where now essentially tr is equal to c squared t minus r dot v plus or minus r dot v minus c squared t quantity squared minus c squared t squared minus r squared c squared minus v squared, all of that under the square root, divided by c squared minus v squared. Essentially, I just factored out the 4 from the square root and then canceled the 2 in the numerator and the denominator. Okay, so let's move this up. And now let's assume that v is equal to 0. Therefore, the retarded time is t plus minus r over c. Take the minus sign in the previous equation right up here. Take the minus sign right there. And what we would get is r is c t minus r sorry, this is a script R right here. And what we would get is R hat is equal to R minus V TR over CT minus TR. So we're kind of coming at this from two different directions. And what we would get is R times 1 minus R hat dot V over C is equal to C T minus TR 1 minus V over C dotted into R minus V TR over C T minus TR. Okay. So basically you just, factor out that C times delta T. And what you get is C T minus TR minus V dot R over C plus V squared TR over C. And we're going to reduce it one more time and essentially take out a C. So I have 1 over C, and I get C squared T minus R dot V minus C squared minus V squared TR. And now what we want to do is take that TR from the quadratic equation and plug it into this equation right here. And in the end, what you should get is 1 over C, the square root of C squared T minus R dot V squared plus C squared minus V squared times R squared minus C squared T squared. Okay, so now it's written it's written entirely in T, time now, and R and V. So now if we plug that into the Leonard-Weichert potentials from the previous lecture, what you get is something that looks like V is 1 over 4 pi epsilon naught QC over C squared T minus R dot V quantity squared plus C squared minus V squared times R squared minus C squared T squared, and close the parentheses, and then the denominator is a square root. Okay. And finally, for the magnetic potential, what you get is mu naught over 4 pi, and then you get Q times C times V, all of that over C squared T minus R dot V quantity squared plus C squared minus V squared times R squared minus C squared T squared, again underneath the square root. So it's looking kind of messy, but what we eventually have is this equations for a single point charge moving with a constant velocity v, which is now given us these potentials, these time-dependent potentials.